Welcome to the ENME 351 video lecture series. This is part one of a three-part installment in which we'll take an introductory look at sensing. In this lesson, we'll introduce the concept of sensing. A sensor provides an output that corresponds to changes or events that occur in the environment in which the sensor is operating. Now, sensors are in fact transducers, where transducers convert energy from one form to another. Transducers, however, they can also be actuators, so they can take some electrical signal and actuate, say, a motor to perform some task in its environment. Consider here a sensor operating in an environment with a measurand, where the measurand is a physical signal that the sensor will detect. So that might be something like light or temperature or pressure. So we have our sensor in our environment, and we'll typically connect that sensor to some sort of interface electronics. These interface electronics, they're typically performing tasks like amplifying or filtering a signal such that we can focus in on the components of the signal of interest. And then from these interface electronics, we'll typically go to an analog to digital converter or a microcontroller similar to what you have on your Arduino. The analog to digital converter, that's allowing me to digitize my signal and permitting me to explore that signal, analyze that signal further on something like my computer. So this is the pathway of our signals in our sensing operations, and we have multiple signals in various forms along the way. We have the measurand, which is a physical signal. The output from the sensor itself might be something like a resistance or a capacitance or a voltage. And it's these interface electronics that are converting, say, this resistance to something like a voltage or a current that you could potentially measure on an analog to digital converter or a microcontroller. So let's take a look at a quick example of this signal pathway. Here is the cadmium sulfide light sensor. This is a photoresistor, and you should have one of these in your parts kit. So this is a CDS light sensor, and based on some change of the intensity of light, we'll actually see a variable resistance. So in this sense then, the resistance of my light sensor, that's dependent, that is changing based on the intensity of the light that's actually incident on the surface of my light sensor. So we could go directly from our light sensor and we could create some interface electronics that would get me some sort of signal that I could actually read on something like my Arduino. In this scenario, I'm interested in getting a voltage signal. So I could set this up as a relatively simple voltage divider. Here we have ground on one end, plus 5 volts on the other. Connected to 5 volts, I have a resistor, and then between that resistor and ground, I now have effectively a variable resistor, that being the photoresistor, my light sensor. And then I have an output voltage, V out, and that'll be coming out of the middle of my voltage divider. From my interface electronics, I could send the signal over to an analog to digital converter or a microcontroller, something like that on my Arduino. And of course, if I really wanted to get fancy, I could have a serial signal connected to my laptop. And using processing, I could actually display some sort of information. I could communicate some sort of information to the user. This is a relatively simple pathway, but this describes the signal paths for this light sensing sensor, this photoresistor, connected to my interface electronics and then to my microcontroller. But now let's take a look at trying to perform a slightly more complicated measurement. Here I'm attempting to measure acceleration. Turns out it's really difficult to measure acceleration directly. So we may require a couple steps, multiple steps, to go from the measurand of interest to something that can actually be sensed. So here we might be interested in measuring acceleration, right? And that's typically in units of something like meters per second squared. But I can't measure that directly. Now I can calculate a force, that'll be in newtons, but maybe I can't even measure that directly either. So what I can measure directly is displacement, and that will be in meters. So in this example, I'm going to measure displacement, but I'm actually going to calculate, based on known parameters, the acceleration, right? So the measurand of interest here is acceleration, and I'm going to back that out from my measurement of displacement. An example of a sensor design that might perform this operation is shown here. This is a mass on a spring. So if I apply a force on this mass, and my acceleration will be related to that force through the mass, and I look here at the displacement, in this case x, I also know that F is equal to k times x. And so with these two equations together, I can calculate the acceleration. That'll be a equals k times x over m. So x is ultimately what I'm measuring in this setup, while k and m, they're known constants. So an example of a measurement for x, this might be some sort of capacitance output, right? The capacitance is changing with respect to the acceleration on the mass. So I'll need to design some interface electronics then to convert that capacitance to a voltage that can then be digitized by an ADC on a microcontroller. Let's take a look at some of the parameters that are going to be of interest, some metrics of interest, when you're choosing a sensor for a particular application. The list here, this is actually a summary list of some of the more important metrics. And we'll summarize them now, and then we'll explore each of these metrics in further detail in subsequent video lectures. Sensitivity we typically define as K, and the sensitivity will be equal to the ratio of output over input in our sensor. So for example, if I have an output in resistance and an input in temperature, I'm going to end up with units of ohms per degree C or per degree K. In another scenario, if I have an output in volts and an input of pressure, I'll look at a sensitivity that will be in units of volts per Pascal. The range, we'll define that as R sub I, so that'll be the input range. And R sub I is equal to the maximum input that the sensor can handle minus the minimum input that the sensor can handle. And you'll often see this listed or described in terms of decibels, dBs. Accuracy, that's going to relate to the expected error. And the error, that'll be described as the measured value minus the true value. So for example, let's say I had a ground truth, some temperature in my system at 50 degrees C, and my sensor is measuring 51 degrees C, right? That'll give me some idea of the accuracy of that sensor. For the resolution, we're looking at the minimum signal that our sensor can detect. And the resolution is typically defined as the noise level in my sensor divided by the sensitivity of my sensor. Noise in this case, that's going to be everything showing up in my signal except for the true signal that I'm interested in. The bandwidth of my sensor, that's going to describe how fast I can sense a particular measurand of interest. While things like size and integration, that's ultimately answering the question, does this sensor fit into the design of my system? And then for power, we're mostly interested in the power consumption. And that's going to be described in terms of watts. So certainly all of the metrics listed here, as well as likely other ones that are of interest to you for your particular application, you should be able to look these up and identify the values for each of these metrics on a datasheet.